Good evening to all. Today we are going to discuss about thermodynamic process for isothermal process and which is used for the real gas. So I'm sure this video is going to be very interesting. So please do keep watching until the end and please subscribe my channel and don't forget to hit the bell icons. Thank you. So let's begin the discussion for a very important topic for isothermal process used for the real gas application. Before that, let's understand thermodynamic systems. So thermodynamic system is mainly related to gas. Gas can be air and or any hydrocarbon. And these are the sign convention. Heat is added is considered positive to the system. When heat is removed is considered negative. Similarly, work done by the system or gas is positive when work done on the system on gas is negative. When the energy level of gas increases, that means energy level of system increases is positive. When it decreases, it is considered negative. This is as per the sign convention, as per first law of thermodynamics. Real gas equation K is written P is equal to Z and RUT and Z is a compressibility factor. So once further simplification, we can write P small v is equal to Z RT, and this is the standard equation which is used for derivation purpose. Types of thermodynamic system: open system, closed system, isolated system. In case of open system, you can see there is a mass flow or mass transfer occurs. Gas comes in and goes out, and as well as energy transfer occurs. In case of closed system, mass transfer doesn't occur, but only energy transfer occurs. In case of isolated system, neither mass transfer occurs nor the energy transfer. Work transfer on PV diagram for closed system, work transfer on PV diagram on open system. In case of closed system, area under the curve on PV diagram on x-axis is equal to work done, and by formula you can use integration of PdV. Similarly, area under the curve on y-axis for PV diagram for open system is equal to the work transfer for the open system, which is equal to minus integration of VdP. So these are the two formula used for the closed system and open system. And as per sign convention, work done by the system is positive, work done on the system is negative, and work transfer per unit mass is called work head or head. Energy transfer for the closed system is equal to in change of internal energy, and change of internal energy is written as integration of CVDT. So energy transfer for the closed system can be written as equal to integration of CVDT. Similarly, energy transfer for the open system is equal to the enthalpy change, and enthalpy change is expressed as integration of CPDT. So energy transfer for the open system is equal to integration of CPDT. Energy of system increases is positive. If it decreases, it is negative. This is again as per the sign convention. And as per first law of thermodynamics, heat transfer is equal to work transfer plus energy transfer. So Q is equal to W plus C. And but the most important assumption for the first law of thermodynamics is system is that the efficiency of the machine is considered 100%. That means there is no losses during the transfer of work. There is no losses during the energy transfer and or heat transfer. So the process is considered ideal and efficiency is 100%. With that assumptions, heat transfer is equal to work transfer plus energy transfer as per the first law of thermodynamics. Now isothermal process, you can see in PV diagram and TS diagram when the expansion process occurs, volume increases, pressure drop. In compressor action process occurs, volume decreases, pressure increases. Similarly, on the TS diagram, you can see temperature entropy diagram. And in isothermal process, energy transfer doesn't occur because temperature is same. Inlet and outlet temperature remains same. Work transfer for the closed system and PV diagram, it is shown on area under the curve on x-axis is equal to work transfer, and work transfer can be derived. Temperature remain constant, so T is equal to T1 is equal to T is equal to T1 is equal to T2. And real gas equation PV is equal to ZRT, so P1 B1 is equal to Z1 RT1, P2 B2 Z2 RT2. Real gas equation CPDT K is equal to CP by CV, and by formula W is equal to integration of PdV, and so P is replaced ZRT upon V, and so we can write after integration Z1 RT1. Ln means natural log, short form it is written Ln V2 by V1. So work transfer per unit mass W is equal to Z1 RT1 ln V2 by V1. If you want to calculate the total work transfer, multiply with mass. These are the two equation for work transfer for the closed system. Now energy transfer, since there is no change of temperature, so energy transfer per unit mass will be 0, and also total energy transfer will be also 0. As per the first law of thermodynamics, heat transfer Q is equal to W plus E. So since E is 0, so we can write Q is equal to W. So Q is equal to Z1 RT1 ln V2 by V1. So this is heat transfer for the per unit mass, and to total mass just multiply with the mass. So total heat transfer is just multiply with mass M. So area under the curve on TS diagram on x-axis is equal to heat transfer. You can show here. This can be shown here. Now isothermal process in open system, temperature is same. PV diagram, area under the curve on y-axis is equal to work transfer. So same way we can write W is equal to minus VdP, and V is replaced at RT by P. So further minus Z1 RT1 natural log P2 by P1, or minus is replaced by changing ratio of P1 and P2. So W is equal to Z1 R T1 natural log P1 by P2. This is equation for work transfer per unit mass. Total work transfer just multiply with mass. So this is shown on PV diagram for work transfer. Again, energy transfer for the open system will be 0 Cp dt. There is no change of temperature. So this E0 for per unit mass, even total mass is also 0. As per the first law of thermodynamics, Q is equal to W plus E. Here E is 0, so it is equal to Q is equal to Z1 R T1 natural log P1 by P2. This is for heat transfer per unit mass, and for total mass just multiply with, for total heat transfer just multiply with mass. TS diagram, which is area under the curve on x-axis, is equal to heat transfer. Now let's understand with the isothermal process for closed and open system. So nitrogen gas has initial pressure and temperature are 0.5 bar gauge and 30 degree Celsius respectively. Gas is compressed such that the final pressure reaches 2.8 bar gauge on constant temperature process with consideration of real gas. Calculate work, energy transfer, heat transfer during this process for considering closed and open system. Also calculate the inlet and outlet specific volume. Following data are given: mole weight of nitrogen 28, universal gas constant 8314.5, specific heat capacity at constant volume, constant pressure 20.88 and 29.26 respectively. Compressibility factor at inlet and final condition 0.999, and both are same. And local barometric pressure is 1 bar absolute. So now these are the closed system, barometric pressure, temperature. So we can convert inlet absolute pressure by adding this 1.5, temperature 30 degree, P2 absolute pressure 1.8, and mole weight Z1, Z2, CV, CP, RU all are given. Now calculate R is equal to RU by M, and CPC is also calculated by dividing by M and multiplying 1000 for converting joule per kg per Kelvin. And then for K Cp by Cv is calculated, then V1 is calculated, V2 is calculated, W is calculated, which is minus 16, that is 16,396. Energy transfer is 0, so heat transfer is same, that is minus 16,396. Open system work transfer is minus 16,396. Energy transfer is 0, so heat transfer is equal to minus 16,396. So I hope you have enjoyed this session. Thank you. Thank you for